but it's okay. You can read it. Light proton-rich nuclei structure using 3n-cluster reaction and the quest for resonances in 6 beryllium. Please.
Okay, thank you. First of all, we'd like to thank the opportunity, the invitation, and I just changed a little bit the title of the talk by including this question for resonance in beryllium-6. So the idea, of course, is to investigate this cluster structure. I'm not going into details. I like very much this slide because you see, all these kind of cluster structure you can have in this light nuclei. And the main problem or the main investigation is how we go from the many body no correlation to few body clusters excited states. So that's all the point we do, all the work we do. The idea here, okay, we have this light nuclei, some of them has one proton halo, one neutron halo, two proton halo, two neutron halo. So these are the most colorful, the most interesting ones. So of course these here are the well-studied, so people are putting a lot of effort to investigate the structure of this here. But as Daniel Phillips said yesterday, so the people are now pushing to produce more and more exotic nuclei, more richer neutrons, richer protons, so on. And so there are several others which can also have these two halo or one halo proton or neutron. But anyway, this neutron side, they can get more attention, but also the proton-rich side is also interesting. So there are several of these light nuclei, proton-rich, which are kind of interesting nucleus. So like the famous boron 8, but also we can have carbon 10, nitrogen 12, and fluorine 17 as a candidate. Here in the figure, it's shown like one proton halo, but most likely they are candidates, so there's not exactly firm confirmation of their halo structure. But anyway, we can have carbon 9, nitrogen 11, oxygen 13. All these drip line proton-rich nuclei are also interesting. The idea how to reach them. So one possibility is exactly removing neutrons from the stable ones and reach the proton-rich side. And we can do that by transfer reaction. And when you do this helium-3, helium-6, you are exactly taking out 3 neutrons. And these 3 neutrons can come out as a cluster, so a 3-neutron cluster. And in case you have this transfer reaction, we can investigate the spectroscopy of this residual nucleus, either by investigating the L transfer in the reaction, but also getting this exactly the energy of these states, and also by doing some DWBA calculation to the angular distribution and get the spectroscopic factor. So we can combine all this information, and then we can investigate the structure of this proton-rich nuclei. So that's exactly what I did. So I investigate some of these reactions. So this particular helium-3, helium-6 reaction has been used a few times. So at the beginning, the first one was my supervisor, Kubono, who first used it to do this kind of spectroscopic investigation. But later on, for my PhD thesis, I did this helium-6, helium-3 on neon-20, and also on nitrogen-14, but also the other guys did some of the same reaction, but for applying to the other nuclei. But we could investigate all these proton-rich nuclei, including the beryllium-6, which was the last measurement of this reaction I know. It was a work for these guys from Russia, and they published it in China reviews, Chinese Physical C. But anyway, for this nitrogen-11, for the for the neon-20, so the neon-20 has 0 plus ground state. This is 1 plus, this is 0 plus. So we can use only the transferred angular momentum of this reaction to get information about the spin and the parity of this residual nucleus. So even if the nucleus is unbound, we still can get information for the states, we still can get the information about the angular moment transferred, because what we are detecting is the helium-6 particles. So here is the energy spectrum. So we have several states from the ground state up to 6 MeV. And I could get the angular distribution for each of them. And the very interesting point is all the angular distribution has a very clear structure corresponding to the L transfer. So each one corresponded to only one L transferred. So you can put in here this L transfer and get 2 possible spins. And by looking at the mirror nuclei or the analogous states, we can get the information about these spins. So that was a very nice work because we could get this spectroscopy for several states in neon 17. And of course, at that time, the importance for this was to see, the change in the levels, like formation of new magic numbers, or inversion of orbital. So the orbital could invert, which means here is the binding energy. So you had the orbital P, P1 half, D is 5 half, here's the S1 half. As you go to lower binding energy, these levels change the position, and we can have also an inversion of the orbitals. But also, you can investigate as you go to richer proton or richer neutron nuclei. You can investigate here the closure of shell model, because when you have this dip here, it means the shell model still holds. But when you have more like straight lines like this, it means this particular number is no longer is a magic number. And for the nitrogen 11, was the main point was exactly to investigate this inversion orbital. So nitrogen 11 has an n equal 4, z equals 7, and this proton could be in this orbital or in this one. And depends if it's in here, the ground state spin would be 1/2 minus. And if it's in here, it has to be 1/2 plus. So the idea is investigate this nitrogen 11 and check if they spin is 1/2 plus or 1/2 minus for the ground state and the first excited state. And it's a situation similar to beryllium 11. So nitrogen 11 is the mirror of beryllium 11. The beryllium 11 was well known to have this spin inversion. So the idea was, is the same hold for the nitrogen 11? And the answer is yes. So we did the measurement. We have this ground state, the first excited state. We get the angular distribution. And the angular distribution also indicates that this is L equal 1 and this is L equal 0, which means for the ground state is 1/2 plus. So at that time, this was a big deal. And so there are several experiments and several measurements just to confirm what is the energy. Nitrogen 11 is unbound. So it's important to know how much is this resonance, what is the energy for this resonance. So there are several measurements, and each one gives a little bit different energy, different values. And the point to see is that depend on the value for this energy of the ground state compared to the fluor 17, we can say if z equal 8 holds as a magic number for proton-rich nuclei or not. Depends if this is like this or this is like that. So it means z equal 8 is still a magic number or not. And the answer is that if you consider the lower values, so the lower values indicate that z equal 8 is still a good magic number for proton-rich nuclei, or at least for these proton-rich nuclei. More recently, these guys from Russia, they did this measurement, beryllium 9, helium 3, helium 6. So the beryllium 9, the ground state has a 3.5 plus spin, so it's more complex, so I cannot do that no longer, no anymore. There are too many combinations of the spins, but anyway, we can try to do some investigation of the structure, in particular for the beryllium 6. So they did a measurement. Here's the angular distribution for the ground states, beryllium 6 ground states. They consider directly helium 3 transfer, so you get a helium 3 transfer here becomes beryllium 6, and left helium 6. So it's a helium transfer, but there's also a possibility to have a 3n transfer. But they did not consider that. They considered the sequential transfer. So they first decided it's a possible 2n and n or n or 2n transfer and the helium-3. They did not consider the helium-3 as a directly clustered transfer. I decided to do this calculation. And here is the result for this line here is for the 3-neutron transfer as a cluster, and here is the result for a helium-3 transfer. The result I get is a little bit different from what they got, and I'm still trying to figure out why. I mean, I did a DWA calculation considering a helium-3 transfer. That's what I got. Of course, there is this amplitude, the spectroscopic amplitude. I have to normalize it somehow. But the shape is different. The shape I got is different from what they got. And I don't know the reason. I may contact them and try to see if we can reach an agreement. But the important is, there's also the possibility to have the 3 neutrons transfer. Maybe this reaction is a combination of the two. So we may try to do this combination of these two mechanisms. Well, the point is, the beryllium-6 is quite interesting. We are going to have a particular talk, a specific talk on this beryllium isotope, maybe on Thursday. I just want to show this slide. So this slide shows how interesting is the beryllium isotope. You can have the beryllium-6, which is a proton-rich, which can decay by 2 protons, so it's interesting to investigate the 2 proton decays, but also the helium-3 molecular structure, which has some implication in the astrophysics I will show you. But also, all these beryllium 9, 10, and 11, they have a similar configuration where you have this n. Here is 2n, alpha 2n. So we had no neutrons, 1 and 2 neutrons, and also beryllium 11. So beryllium 11 can also have this 4-neutron cluster, in beryllium 12, sorry. And the beryllium 11, beryllium 14, beryllium 16 are considered 1 neutron or 2 neutron halos. So all the isotopes, each one has some interesting physics behind it. So let's wait for the talk. Now I will concentrate, I will focus on beryllium-6. So from this, beryllium-6, many years ago, they considered the possibility to have a nuclear explanation for the solar neutrino, which means that if you have some resonance in this helium-3 reaction, we get more of this cross-section and less for this branch of the PP chain. And if we have less here, we have less solar neutrinos. So one possible explanation for the solar neutrino was the possibility to have a resonance in this particular reaction, and in particular in the helium-3, which corresponds resonance in beryllium-6. So there is a interest in investigate beryllium-6 and see if there is this such resonance at 11 MeV. Sorry, I have to go back. At 11 MeV. And also, here is the direct measurement for this reaction. So this helium-3 to P helium-4 reaction was measured at the Gran Sasso. So they have a direct measurement at low energy. So you see the low energy is a mass. The error bar is too big. But the point is, if we consider the electron screening, that's what we should get as the as the S factor. Or if you have a bare without electrons, that's what we get. The point is to go here to here, you have to know the screening effect. The screening effect is given by this potential, this function which corresponds to this potential. And this potential taken from this data, it has to be 294, and a compilation of several other works is 205, and from the adiabatic model is 240, sorry. So there is some difference here, and this difference here could explain part of these things here. But there is still room for a possible resonance in here, so influence of the resonance. If we decrease this potential, we can consider some contribution of resonance. So the idea is there or not a resonance in beryllium-6? And then I start a kind of question for looking for this resonance. You see, here in helium-6, we have several resonances, and some of them was identified by this work from the people from Osaka University, including lithium-6. Lithium-6, there are two indications. This is just an indication. There are two bumps here, and this bump here corresponds just an indication of this new possible resonance. But anyway, helium-6 is the mirror of beryllium-6. We expect more resonances here. So it would be interesting to investigate if such a possibility for this resonance. Here, this one here was also observed in this last work. So you can see a resonance, a large, broad resonance at about 18 MeV. So it corresponds to a resonance here. But okay, so I start a quest for this resonance. The quest means I performed several experiments. The first experiment in 2002 at Notre Dame, I used a boron-8 deuteron reaction. So there's a deuteron transfer. So if you transfer a deuteron to here, you get helium-4 and beryllium-6. And we use this twin salt to produce the boron-8 beam. And we got a result. I measure 3 or 4 angles only, and only one of them has an indication of a possible resonance in 11 MeV. But I cannot say for sure about this resonance, and well, maybe we needed to do another measurement. So that's what we did. We did another measurement in Oak Ridge before Oak Ridge was shut down. So that was in 2004. And we use the beryllium-7D experiment. So beryllium-7D is a neutron transfer. You get beryllium-6. Beryllium-6 decays by these two possibilities. And we have several detectors. And here is the particle identification. And we had a problem here. Helium-3 is too energetic. So we have too energetic helium-3 punching through. And even if you use a veto detector, which corresponds to helium-3 punching through all the detectors, use the last one as a veto, you still could get some influence in the triton spectrum. So here's the triton spectrum. So several angles. So the one which can give the 11 MeV excitation energy is only these two here. We have some bumps, which could be the resonance, but the problem is this bump is exactly in the same region as this helium-3. So we cannot rule out the possibility to have a helium-3 contamination in this spectrum, and there is nothing we can do. So all we can do is to do another measurement. Yeah, so that's actually what we did. So we went to Japan, and we did this experiment, beryllium-7 helium-3. So it's also a neutron transfer reaction, beryllium-7 helium-3. So we have the alpha, so we detected the alpha. So we use the strip to get the beryllium-7 beam. We use a gas target, and there's 3 detectors, 3 large detectors, this DSSSD detector 5x5. And here is the particle identification. So we have cleared the helium-4. So if I can get this spectrum from the helium-4, we can get the excitation energy of the beryllium-6. So here's the result. So right now, that is what we get. So this is the spectrum. We have some indication for resonance here, indication for resonance. But again, it's just an indication. I'm finishing. This work we are working on it right now. So we just finished this background. This is a 3-body phase background, but we have to calculate the 3-body background, which is a background here. So I have to do a phase space background, subtract this background and see what is left, and try to do some aerometric calculations. So this is a preliminary result, so we are still working on. But anyway, there's indication of resonance here and here. Again, it's an indication. I cannot be completely sure, but so what we can do a better job. I can do a better experiment. The best way to do this kind of experiment, where you have so many particles come out, is by using active target. So in active target, you detect everything. So in active target, you have a gas. The gas is the target and the detector. So you ionize the gas. The electrons are drifted to the pad plane. You get information, you get some amplification of the electrons here, and then we get this pad, so we can exactly get the trajectory, the tracks of the reaction. So this we would be able to get all the reactions, all the tracks for all the reactions. So we did this experiment in argon. So we proposed this experiment in argon in 2023, so we still are working the data analysis. It's a quite heavy analysis to get out something from this active target. And even more complicated because we put this active target inside the helios, which is a solenoid. So we have an active target inside the solenoid. So here is active target inside the solenoid. And here is a simulation, so in principle we can get all the particles. And because it's in the solenoid, the trajectory inside the active target is helicoidal, like this. You can make a projection in this pad plane, and the projection in this pad plane gets these curves here. And by getting information of these curves, we can get the particles, the angles, all the kinematic information of the particles. So this is a kind of a rigidity, a B-row, so we can get particle identification and all the kinematics only by analyzing this spectrum. And this is the preliminary results for this. So these preliminary results from this reaction, beryllium-7 on deuterium, but also we have some lithium-7, a part of a primary beam is still punching through and going to the active target. So we also get data from lithium-7 on deuterium. So we can investigate the structure of a beryllium-8, lithium-8, lithium-7, beryllium-7, lithium-6, and beryllium-6. So the idea here is kinematic, so it's energy as a function of angle. And as you go to this direction, it means you get excited states. So this is ground state, and this is one is 18 MeV. This one is ground state, and this one is 7 MeV. And for lithium-7, we can clearly see the ground state and some other states, ground state and some other states. We still have to clean up this spectrum, make the projection to get the energy spectrum. So it's still preliminary results. But we can see for the lithium-6, it's very well defined, so we have the ground state and the possible all the other states. We are going to clean up a little bit better here. But for the beryllium-6, which is what we have an interest, is we hardly see something. Maybe there are too many, the probability or the cross-section is too small. So we get few things here, but we still have to work more on this data to see if we actually can see something. Of course, in these excited states, we can have still the two protons decay, so we can also investigate the two protons decay. We are not looking to the two protons. Right now, this is a triton spectrum. Once we look into the two protons, we can also investigate the beryllium-6 two proton decay. So there is still a lot of work to be done in this data. Also, using the same idea of active target, so this is ACTAR, we also did in 2004, so we're still working on this data, an experiment related to the 4n transfer. So the experiment in Ganil was performed to see the resonance in beryllium-12. So we have a helium-8 beam on a helium-4 target, so it's active target filled with helium-4 gas. So we have, if we have a resonance state, we can investigate the resonance above these thresholds. So mostly we can investigate the resonances nearby 11 or 12 in MeV of beryllium-12. So these resonances can have a different configuration, can be helium-6, but also can be helium-4, helium-8. All these channels, all the thresholds for all these possible channels are around here, so we can check, by analyzing the data, this excitation energy region of beryllium-12. Here's some preliminary results. So the preliminary results by getting some slides here for a particular angle. So we got this spectrum, and this spectrum shows 3-4 resonance. So we still are working on it, but one of them is very clear to 12 MeV, but there's some others. So there's a student right now working on this. So very soon we may have some better results to show. So also, out of this beryllium-12, there is a possibility to see this 4-neutron cluster. So the helium-8 would, the final state would be alpha and alpha, and this 4n, this 4n as a cluster, and then would be the confirmation for this tetraneutron cluster. So we can extract this out of this data, but still it's going to have some, we need more time. I just finished. So thank you.
Thank you very much for this interesting talk. Questions? Comments? If not, I have a comment, because I remember vaguely that I think 30 years ago we published correlation functions on different particles in heavy ion reactions, alpha D, alpha alpha, what have you, lithium, in order to observe lithium-5. And I vaguely remember that we also published a helium-3 correlation function. And as far as I remember, we can look at the paper together, there was no resonance there in that state, in the system.
So I'm looking for something which is not there.
So maybe this is even the more ideal case to look for resonances, because you see all the other resonances in boron, etc., in these correlation functions. Other comments, questions?
But please, can you forward the
Yeah,
paper?
I can.
Because I don't know if I
Yeah,
remember,
sure.
if I saw it.
Yeah. No comments? No questions? Okay, so let's thank the speaker again.
Thank you.